All right, we are going to start with some geometry with chapter 11, and section 11.1 is primarily vocabulary. So sit back, relax, get your fingers all warmed up for all the vocab we're going to be looking at today. What we want to take a look at first of all is a point. Now in geometry, a point is always denoted by a capital letter, right? A point has no dimension, and I'll come back to that in just a moment. So make sure it's always a capital letter. Lowercase letters represent line segments. Now, a line, often used with a scripted L, a cursive L, is represented as passing through the 2 points we're talking about. So the symbol you'll see is either from point A through point B or through point B, A. So a line has one dimension. It's just going. Okay? And a plane is two-dimensional. And a plane you'll either see denoted as the word plane, ABC, or you'll see the Greek letter gamma. Okay? And a plane, oftentimes when we try to draw a plane, think of a parallelogram where they'll tell you that it has 3 points on it. It doesn't mean it's a triangle, it just means 3 points. Okay? So a plane is two-dimensional because it has like a length and a width. A line is one dimension because it just goes. And a point technically is no dimension. A point just exists. Okay? All right. So as we talk through a lot of this vocabulary, we're going to look at differences between, for example, you might hear something called an axiom or a postulate. An axiom is a statement which cannot be proven. We assume that it's true. Okay? It is assumed true. Now in high school geometry, you may have also heard postulate, same type of thing. All right, it's a statement which cannot be proven. We assume it's true. When we can prove, that's what we call a theorem. These are statements which can be proven. And we have various tools we use when we prove a theorem, okay? So these can be proven true by using, and let's talk about what they can. Well, we can always use a definition, which is where we usually start with, like when you're annotating, start with what you know, start with a definition. We can always use a previously proven theorem. We can prove a theorem using constructions, which we will be using in this class. And logic, which we've also done some with, especially the prerequisite for this class. So when we go to prove a theorem, you can always use a definition. So look at your vocabulary. We can always use anything else that we've already proven true. Construction, so we'll be doing some drawings that are very precise. In constructions, you need a straight edge and a protractor, or I'm so sorry, a straight edge and a compass for, and then logic. Okay. Now, since we're going to start off talking about a little bit of lines and planes, let's take a look at what we mean by definition of collinear points. Okay, collinear points. And that prefix co usually means with. So these are points which lie on the same line. How far? Okay, I can go a little further. All right, so any 2 points that are on the same line are considered collinear. So an example of that might be the following. Here's a line. You can think of the number line. It's a great example, but we do not need to put numbers on it. A line has a symbol on each end saying it goes forever and ever and ever. But let's say I put 3 points. I put the point A, I put the point B, and I put the point C. All right, so those would be considered collinear because they're all on the same line. All right, and we can also look at some properties from algebra, because we need to talk about what it means if we look at the word between. And I'm using between in a geometric manner. Between still has the same implication, but if I look at this line that I did before up here, I might as well refer to that one. I can say that, how do I want, if line segment AB plus line segment BC, notice they do not have arrows on the ends of them because they're a segment. If I add these two together, the distance from A to B and B to C, that's the same as going, starting at A and ending at C. This is the transitive property. If this is a case, then we can say the point B is between point A and point C. And then I made reference to a line segment, so let's take a look at an actual line segment. And you can think of a line segment as being part of a line. Part of a line. Okay, it contains or has endpoints. So we have a starting point and we have an ending point. A line segment, since it's part of a line, it's a subset of a line. So if I give you a line, okay, so here's a line, and I give you 3 points again. I'm going to give you point A, point B, point C. I can say that we have line segment would be represented from A to B, starting at A, ending at B. Or I could have line segment AC, starting at A, ending at C. We just ignore B in the middle. Or we could have line segment BC. Or we could go the other way around. We can say CB. Right? Order doesn't matter. It just tells us where we start and where we finish. Okay. And then I'm going to wrap up this little part before I erase. with talking about what's called a half open or half closed segment. Half open, some people prefer half closed segment. Okay, kind of like the glass is half full or half empty, kind of depends on how you look at it. So if it's a segment, we know it should look like a line segment. But if it's half open or half closed, that means I can start at a point A and finish at B. Well, perhaps I don't actually touch point A, but I do touch point B. So I would leave an open circle to indicate that the point is actually not including A, but is so close to A that it has this little protective opening around it. Or you could say perhaps it starts with A, but it doesn't actually touch B. So you may remember in algebra classes, you might have had inequalities. So we had that open circle. So that's just called a half open segment or a half closed segment. Okay. Whereas if you have an open segment, this implies the whole thing is open. So you probably already made a prediction. That means if I'm starting at A and I'm ending at B, if it's an open segment, it doesn't touch A and it doesn't touch B. So they're both open. So it's as if you said like greater than or less than, but it's not equal. It's just open. Okay. All right. Again, heavy vocab. It's pretty much all vocab, this particular section. All right, so let's move on and we're going to take a look at what's called array. And when I introduce it to students, especially for the first time, I talk to them about like a sun ray. And think about when you were in elementary school, you don't need to write this down, but you remember in elementary school, if the teacher, if you drew a sun, you always started with your sun, and then you went out from there, and you always went out and you made your sun kind of look like this to indicate that the sun shone in every direction. Well, that's a nice way to introduce array to a child. So array is also a subset of a line. But with array, you start at a single point, okay? We start at a single point, and then we go out from that point. So I might start at a single point. I'll call that A. I'm going to tell you it's going to pass through another point. We're just calling it B. But then I put the arrow on the end to indicate that it keeps going. So kind of like a sun ray. And so the symbol for array is, I have to tell the starting point, I have to mention the point that it passes through, and I just indicate the arrow that's passing through B and continuing forever. And you can make sure this is a solid point if you want, because it has to start at a solid point. Okay. Now those that are familiar with physics and vectors, a vector symbol looks a lot like array, but it only has one little arrow part. So it does look similar to a vector. Okay. And now let's talk about what we mean by opposite rays. So these are going to be rays, which is also, part of a line. And opposite indicate that they go in opposite directions. So opposite meaning that they are 180 degrees apart. So the angle between the rays is exactly 180 degrees. So if I'm drawing that, well, that would mean that I would start with one ray. So maybe I have this ray right here, and maybe this is going from A through B. So there's a ray. But now the angle between them has to be exactly 180 degrees, which means that this is heading in the exact opposite direction. And so now I'm going to have it pass through another point, C. Okay. So that's what we mean by an opposite ray. So I would say ray AB, and starting with A again, are opposites. Okay. All right. Okay, so let's now that we've talked about some lines, we've talked about subsets of lines, let's move on to some of the planes. Instead of one dimension, let's take a look at two dimension planes. Okay. So let's take a look, and we'll look at planar notation. So we're taking a look at planes. Planar notation. So we just earlier talked about what a plane looks like. Now let's really look at the definition. All right, so a plane, by definition, is a two-dimensional space. It's two dimensions which go infinitely in those two directions, okay? Two dimensions which are infinite. It has no thickness. All right, so no thickness. So a great example is to talk about this whiteboard or a tabletop. And I know you're thinking, well, a tabletop has dimension, but if we're just looking at the surface, that surface theoretically can go on forever in every direction. So the easiest way is to talk about a wall or the chalkboard you're writing on or a piece of paper, and just have students imagine that that goes on forever, okay? But we talked about drawing it, and I'll do it again. If we draw a plane, we usually take and kind of draw a parallelogram. Opposite sides are parallel, but it doesn't have to be. And we usually put 3 points on them. So we might say this is point A, we might call this point B, and we might call another one point C, and we would just call this plane ABC. But the idea is it's going to keep stretching forever, right? So we talked earlier about something called collinear. Now let's talk about coplanar. So coplanar, again, that prefix meaning with, this indicates that these are points which lie on the same plane. So anything I've drawn on this board would be coplanar. This C, this A, this B, these over here, anything, because they're on the same surface. Okay, and let's then kind of go back and take a look at lines. So we're just looking at vocab. Intersecting lines. Because now we can put these in terms of a plane. So intersecting lines have exactly one point in common, and they have to be on the same plane, okay? These are lines which have only one point in common. And these lines lie on the same plane. So I'm going to go ahead and say, you know, the lines are coplanar. So I can add to the previous definition because I could have said coplanar points, coplanar lines. So you know what, I'm going to just, instead of writing a second definition, let's just say this could be points or lines which lie on the same plane. So again, if I have this tabletop or I have this surface, any lines that are on the same surface are coplanar. Those are coplanar lines. And then here's a fun word, skew. So if I have lines which are said to be skew, or sometimes you'll hear people say, I feel askew today. Askew, A-S-K-E-W. Askew, well, skew lines are lines which are not coplanar. So these are non-coplanar lines. Non-coplanar lines, meaning, let's say I have this ruler is laying on this plane, but I have my pen coming at a different angle. It's hard to tell on the video, but let's just say this pen is coming down, whereas this ruler is laying across. These are on two separate planes. They may intersect each other, but they may also not intersect each other. So I could have a line laying on the table, and I can have this bottle being resting on the table, and they don't have to necessarily touch. So each of them represents their own line, so they would be coplanar. And I'm sorry, they would be skew lines. Okay. And then let's take a look at what we mean by concurrent lines. Concurrent lines. And concurrent lines intersect at a single point. Okay, so what do I mean by that? Well, perhaps I have a lot of different lines. So I'm just picking a lot of different colors here. What do I have? Black, blue, here's pink, right? So here's all of these represent a different line, and I think you may get the idea here. Each one of these lines, okay, are all intersecting at one point. So these are what we call concurrent lines. I like the pink. Okay. All right, so let's look at an example and kind of look at some of this vocabulary and see how it's going. All righty-o. So I'm going to give you a drawing here. And let's look at an example. I couldn't find the blue. Here we go. So I'm just going to give you a plane. Of course, we're talking about this surface. So just to make it look a little nicer, all right, so here's a plane. Of course, we know it goes forever in every direction. And I'm going to give you a few points on the plane. I'm going to give you the point D, E, G. And then I'm going to give you this point over here, F, which is not on the plane. Easiest way would be to imagine you have these 3 points on the plane and then you just have another point, again, it's hard with a camera, suspending in the air above it. I'm going to write these down. Okay. And I'm going to give you a minute while I erase that side. Name coplanar lines. Name non-coplanar points. Name intersecting lines. And name some concurrent lines. Okay, so look at those for a minute. I'll erase the other side of the board, and then we'll look at them. All right, so let's take a look at the coplanar lines. Maybe I shouldn't have erased, but the coplanar lines, remember, are lines which lie on the same plane. So we have several correct answers, depending on what you happen to see. We could say that we have a line from D to E, or the other way around. It could have been E to D. Remember, with the lines that go on forever in both directions. I could have a line from D to G or G to D. Or I could have the line from E to G. Okay. Now technically there's another plane that's coming out here, but right now we're not really worrying about that. Notice F is not on this plane, so it cannot be coplanar. Now let's take a look at some coplanar points. Well, right now I've only shown the one plane. So the only points that are on the same plane would be point D, point E, point G, in any order. Intersecting lines. Well, if we take a look at intersecting lines, we would have to figure out, do we have any that are intersecting? Intersecting means they just have to touch at one exact point. So I could take a line from D to E, and I could take a line from G to E, and they would intersect at E. That's one example. So I could say DE and EG, or GE. Okay? I said lines, I better make them lines. Or you could do any of these combinations. From D to G, and E to G, Or I think we have one other. Let's see, oh, they both have to intersect at D. So I could say from E to D and G to D, or D to G, okay? And then concurrent lines. And again, same type of idea. Concurrent lines, remember, intersect at a single point. So concurrent lines, we could have the same idea. So concurrent lines, we actually have the exact same thing because they're going to intersect. Or I could call them line segments. But I'm going to do the exact same, since each one would intersect at one point. Okay. So now let's take a look at parallel lines. Remember today, this is all vocab. And elementary school geometry, you probably talked about parallel lines being lines that do not exist, do not touch, so sorry, lines which never intersect. We're going to add to that by just a little bit, all right? We're going to say lines, it can be more than two, lines which are on the same plane, so they're coplanar, okay? So they are on the same plane, which never intersect. All right, so if they don't intersect, they have no points in common. And we have a symbol for parallel lines. I'm going to give you a plane right here. I'll call this plane ABC. So therefore, I'm going to give you points A, B, and C. But I'm going to give you point A, B, and I'm going to give you point C, D. And if these are parallel lines, then I can say, for example, AB is parallel to CD. So they never intersect, and I would end up saying AB is parallel to CD. So make sure your lines, your symbol for parallel lines are parallel lines, and make sure they're longer than the actual letters A and B, C, and D. All right, let's take a look now that we've talked about some parallel lines. We also can have parallel planes. And two distinct points, well, let me do this first. Let's do this. While we're talking about parallel, let's take a look at parallel planes. Make a little more room here. Okay. So if I take a look at parallel planes, these are planes which never intersect. So a nice example to give to your students would be like shelves in a bookshelf. I can show you by taking and saying, all right, this whiteboard is a plane, this pad of paper is a plane. As long as they're not resting on each other, they're parallel to each other because they don't touch. Okay, now I can give you two distinct planes, and notice what happens if they do intersect. If I take a plane and another plane, they're going to intersect and actually form one line where they intersect. All right, now in theory, this tablet would go right on through this whiteboard and you would be able to see that it intersects at a line. Okay. So two distinct planes intersect at a single line. So we'll make a little side note. Two distinct planes, such as the whiteboard and the tablet that I was just holding of paper, intersect at a line, at a single line. Okay. All right, well now, okay, now that we've talked about some points, we've talked about collinear points, we've talked about lines, we've talked about planes, we've talked about all kinds of parallel lines, coplanar lines, intersecting lines. Now let's also address angles. So you will be needing a protractor. You can either purchase a protractor or you could go and online Google protractor images, and you could probably print one and cut one out so that you have a way to measure some angles. Okay. All right, so let's take a look at angle notation and angle measures. So first of all, let's take a look at what we mean by the definition of an angle. So by definition, it's the intersection of two rays sharing the same endpoint. And there we go. So it's the intersection of two rays having the same endpoint. All right, so if I'm constructing this, let's say I take and I have an initial side. Here's one ray. I'll call this angle B, or rather point B. I'll call this point C so that we have our ray. And I'm going to make another ray having this, whoops, sorry, my ruler slipped. And I'll say this one's passing through point A. So here's an angle. Now there's various parts of the angle, so let's identify the various parts. The point of intersection is called the vertex. All right, that's the hinge if you want to think about it that way. Now we also have parts and pieces because we have a lot of ways we could refer to this angle. We have what's called the interior part. Here's the interior part of the angle. And everything around the outside would be considered the exterior part of the angle. Sometimes you also hear it referred to as a reflex angle. Okay? Reflex. All right. Now, oftentimes, not as often as you think actually, you're going to see this referred to as angle B because that's the vertex. You might also hear it referred to as the measurement from A to B to C. So sometimes you might see or remember that they'll have a little notation here that just says I've gone from A to B to C. or from C to B to A. Sometimes you also might see it numbered like angle 1. Usually we'll refer to them by numbers, or we'll refer to them by the vertex, or we'll refer to them by the 3 points needed to create the angle. So here's some notation you might see. This could be considered angle B, or it could be considered the angle created from going from point A to point B to point C in that order. Or you could have gone from point C to B to A. Or sometimes they just give you a number, like in this case, the number 1, angle number 1. And then let's take a look at adding an adjective to describe what kind of angles. So let's say we take a look at what are called adjacent angles. Not sure what happened to the sound there for a minute. I apologize. So let's take a look. We've added an adjective. Adjacent angles. So this word adjacent geometrically means the same thing it normally does. It just means next to. So if you're next to somebody, you are standing adjacent. Adjacent angles are angles which are next to each other and they share a common side. All right, so say for example, let's draw some adjacent angles. I am going to draw this angle right here. Right? And for simplicity, I'm just going to put one that goes on the interior of that angle. So I'm going to label a point from A to the vertex B through point C. So I could say angle ABC is adjacent or next to, and let's put D on the other line, because now we can continue where we left off from A to B to C. So there's this angle. And we could leave off from there and go from C to B to D. Angle C, B, D. Or you could have said from D, B, C. But the idea is you can notice that they both go from line segment BC or CB. So they're both sharing the same side. So those are adjacent angles. Right? And then let's talk about angle measurement and where some of these angles come from. So if I take a look at a circle, and actually, you know what? I'm going to use a little more space. So let me erase this so that I don't have to try and fit it all into that little space that's left. And we need to draw a circle. So this is where we will be using a compass eventually, not today. It's not necessary for our definition day. But we want to take a look at what is a circle, how do we come up with some angle measurements, and do a little bit of calculation. So we've now talked about what an angle is. Let's talk about angle measurements. Okay. All right, that's pretty close. All right, so if we have a circle, and let's look at a little bit of vocab, we have a center of our circle. So we have our interior of our circle, our exterior of a circle. We want to first start with what's called the central angle. And the central angle is an angle whose vertex is at the center. Okay, the angle whose vertex is at the center of the circle. So if I give you an angle, a central angle, sorry, it's smearing a little bit. All right, this is my central angle. Here's my angle measure right here. We have what's called the arc. And the arc of the circle is on this part of the circle. I don't want to draw the blue on top of the black because it'll just smear everywhere. But this piece right here, just the part on the circle, is what we call the arc. And the arc is what the central angle spans. So you'll notice this angle comes out and hits this arc. Okay. Now you all probably are very familiar with the fact that a circle has 360 degrees. So what we wanted, let's talk about that. Every circle is equivalent to 360 degrees from the central angle, going all the way around once. 1 degree, so if I only want 1 degree, I would have to divide this circle into 360 pieces. Well, I'm going to also say that's the same as 1 part out of 360, so it's 1/360th of a single rotation. So if I go around the circle once, that's the circumference. If I only go 1 degree, I've only gone 1 out of 360 parts. Now what I'm not sure you know is that every single degree can be broken down into minutes. Okay? 1 minute, this is called a minute, just like on a clock, you guys. 1 minute is 1/60th of a degree. Just like on a clock, it has everything to do with a clock. A clock has everything to do with a circle. 1 minute is 1 out of 60 minutes, or 1 out of an hour. And then we know on a clock that a minute is broken down into seconds. So we use 2 little hash marks to represent seconds. And you all know that there are 60 seconds in every minute. So 1 second is 1/60th of a minute. So before we go on, I want to take the idea of degrees and circle and convert and practice changing. All right? So we're going to do a few little conversions. What I would like to do is to convert 1 degree 45 minutes to degrees. 1 degree 45 minutes. So we want to know how many degrees do we have total. So I'm going to break this up like you would kind of a math problem. Notice I know this is a math class, but think of it as a mixed number problem. I know I have 1 whole degree, so that part's already done. I just need to convert the minutes to degrees. So notice I'm going to rewrite this like a mixed number problem. I have 1 degree plus 45 minutes. So I still have 1 degree, but let's change these minutes to degrees. Well, we know that 1 minute is 1/60th of a degree. So I'm going to take my 45 minutes and I'm going to multiply it by a conversion fact. I'm going to multiply it by the fact that 1 degree is exactly the same as 60 minutes. So I'm doing a little stoichiometry. I'm just multiplying by the number 1. Okay? This is simply the number 1. And you can always multiply by 1 without changing the value. We're just changing the way that it looks. So now what I'm going to do, I already have my 1 degree. Notice what's going to happen. Because these have the same unit of measure, and one's in the numerator and one's in the denominator, these minute symbols are going to cancel each other. So I'm going to cancel the minute with the minute, and I'm now left with 45 degrees out of 60. So if I convert 45 out of 60, that's the same as 3/4 or 0.75. And so I'm left with 1.75 degrees. Okay, so we're going to do it again. I'm going to do it again. Let's convert 8.42 degrees. And this time we want to convert them to degrees, minutes, and seconds. All right, so I'm going to do it in pieces. I like to start off with, well, let's see, what do we know first? We know how many degrees there are. We know we have 8 degrees. So I have 8 degrees plus 0.42 degrees, okay? And what I want to do is I'm first going to convert, because I already have the degrees, let's start converting to minutes. So this time I want to get rid of the degree symbol. So instead of putting the degrees in the numerator, I'm going to say that we know that 1 degree is the same as 60 minutes. So all I did was multiply by the number 1. These two are the same thing, therefore it's the same as multiplying by the number 1. So if I do that, that's going to give me 8 degrees plus, notice my degree symbols cancel. So I'm left with 0.42 times 60 minutes. Well, if I do that multiplication, that gives me 8 degrees plus 0.42 times 60 is 25.2 minutes. Well, let's think about what that says. This gives me 8 degrees. This gives me 25 whole minutes plus 2/10 of a minute. So now I'm going to convert the 2/10 of a minute, because that's less than 1. I'm going to convert that to seconds. So excuse me, 8 degrees, 25 minutes, and now I need to convert 0.2 minutes into seconds. Well, you and I both know that in 1 minute there are 60 seconds. We have that same thing written over here. So if I want to eliminate the minutes, I'm going to say 1 minute is exactly the same as 60 seconds. Now, just like with stoichiometry, just like with reducing, I'm now left with 8 degrees, 25 minutes, and if I do this arithmetic, notice our units of measure cancel with our units of measure, and I am left with 0.2 times 60 minutes. I think I have a little room left down here. 8 degrees, 25 minutes, and if I do that arithmetic, I end up with 12 seconds. Okay, so each time all I did was I multiplied by the number 1. I just made the number 1 either be in terms of minutes and degrees or in terms of seconds and minutes. Okay. So now that we've talked about angle measurement and what an angle comes from, how many degrees there are in a circle, let's look at some angle classification. All right. So angle classification. All right. So yes, this section is very, very vocabulary rich. All right. So the good news is you guys can pause anytime you need to, seeing it this way. So let's take a look at angle classification. So there's a variety of angles. What I like to look at is, let's start with, we have 4 different kinds of angles. Guess I didn't need to make them this large. I just sort of started and kept going, right? And what I'd like to do is give you sort of a reference. Okay, 90 degrees, here's a perpendicular line, just to give you some reference. All right, so when we look at our angle classification, and we can use our protractor or not, but if I lay my protractor down so that this 0 line is right along, I call it a 0 line. You'll notice it comes right up here to 90. If I draw or construct an angle which is less than 90 degrees, so if I take this and I construct an angle right here that's less than 90 degrees, where here's my angle, that is called an acute angle. Okay, the measure is less than 90 degrees. That's what that little m represents, measure. The measure is less than 90 degrees. It's a cute little angle. Then if I keep getting larger and I end up with an angle that measures exactly 90 degrees, so if I keep opening it up, that's what we call a right angle. And the symbol for that right angle is that little square. So the measure equals 90 degrees exactly. Well, if I keep opening up my angle, as I keep creating my circle, and I go past 90 degrees, but I don't go all the way to the other line, this angle that goes past 90 but is less than 180 is what's called obtuse. So that measure is between 90 degrees, is less than that measure, which is less than 180 degrees. And then if I go all the way past, and I come all the way past 90, and I go all the way around to 180, that's what we call a straight angle. So its measure is exactly 180 degrees. And then if I have 2 angles, whether they're adjacent to each other or not, does not matter, right? We want to take a look at what we mean by complementary angles. And these are two angles whose sum is 90 degrees. All right. And here we go, two angles whose sum, so when you add them together, is 90 degrees exactly. And I bet some of you remember what you call them when you add them together and you get 180. Those are called supplementary angles. So this is two angles whose sum is exactly 180. Okay. So now we've talked about angles. I want to talk a little bit about finishing up with circles. So we're going to go with circles and their angle measures, and then that'll be it. We'll call that probably the longest lesson we have in the entire book. So we're going to finish up with circles, and then next time we'll start using some of these definitions and practicing. All right, so the last section, last part of this section has to do with our circles. And I'm going to be freehanding our circles since we're going to be looking at several parts of a circle. All right, notice they are in the book. They might be easier to see in the book, but excuse me, circles and angle measures. So let's make sure we kind of look there. And depending on whether you took a geometry class in high school and how long ago that was, and whether you all covered it, some of you may have seen this before. Some of you may have never seen this before. That's okay. So let's take a look at some of the vocab first. So first of all, if I give you a circle, whoops, not quite round, but please be forgiving. I'll assume your circle's are round if you assume my circle's round. First of all, let's go through parts of the circle. So we have what's called the radius. And the radius is this line segment connecting the center to any point on the circle. Okay. And then I'm going to probably color code a little bit. All right. We have what's called a chord. I guess I should label radius first of all. There's the radius. We have what's called a chord. And it's a line segment connecting any 2 points on the circle. So I'm just going to pick this point and this point. Sometimes a chord could be very short. Sometimes a chord could be very long. And we don't have a symbol for a chord. I'm just going to color code it. And hopefully that will help. Then we have what's called the diameter. So the diameter is the longest chord possible. It's the longest one. The diameter is a chord passing through the center. So it has to go all the way through the center from one side to the other. Whoops. Oh no, I ran into the black pen. Hopefully that won't mess that up too much. All right. So the diameter goes all the way across and it does go through the center. So make a note that 2 radii are exactly the same as 1 diameter. And then we talked about it before, but I'll just sort of put this in. I think the other color you might be able to see easiest is green. So we're going to label the central angle. I'll make sure I say it in case you can't see it. But the central angle is the angle formed at the center of the circle. Okay. And then we already talked about the arc. An arc is created, well, let me write this down. This is the angle formed let's do it this way, having the vertex the center of the circle. And again, all of these, I believe, are in your book, so you can take a look at that. Okay. And we did talk about an arc. I want to talk about the arc again, because we want to then look at some measurements of arcs. The arc is formed, here's the arc, okay? The arc is formed from one point on the circle to another point and is created from the central angle. All right, so the arc on a circle this is always formed or created by the span of the central angle. So I sort of want to bounce off of that a little bit, bounce off of that arc a little bit. So I'm going to draw a circle and I want to kind of practice some measurements, all right, with some examples. So if I give you a circle, oh, that one's a little better. There's my center of my circle. And we talked a little bit about how to create the angle and the arc. I'm going to tell you that the center of the circle is labeled O, and I want to give you 4 points on the circle. Okay, let's go with point A, and I want to make D exactly across from it so that it becomes the diameter. And then I'm going to call this point B, and I'm going to call this point C. They don't necessarily have to be the same. And just for reference, here's my diameter, so it goes through the center. And then I'm going to create these other interior central angles that are using the center as the vertex. And then I want to practice. And I want to do this, I think, with colors. I think it might help a little bit with color coding. All right, so if I start with central angle, and then over here I'm going to have an arc. So if I give you central angle, angle A, O, let's go AOB. Just start at the beginning. So notice angle AOB, A to O to B, is this central angle right here. It will span, and its degree measure is exactly the same as the measure of the arc formed from A to B. And the symbol for an arc is kind of like a rainbow. It's an arc. So I can tell you that if I know this measurement is 60 degrees, I know this arc between A and B is also 60 degrees. So the measurements are always the same. The measure of the central angle will always be the measure of the arc that it spans. So let's say I give you BOC. I give you, and I'm putting it in green. Well, the measurement of that central angle from B to O to C will be exactly the same as the measure of the arc that it spans. So again, whatever that central measurement is, that angle measure is, that arc measure is. So following this up then, if I give you the diameter, well, let's think about this. The measurement of AOD, which we said was the diameter, well, the diameter goes all the way across. We already know its measurement. Its measurement is going to be 180 degrees. It's going to be the measurement of arc. And watch how I write this arc. I can go from A to D this way, or I can go from A to D this way. Either way, for the moment, I'm going from A to D. And because it's a diameter, we automatically know it's 180 degrees because it's passing right through the center to the opposite side. Okay. So bouncing off of that, we want to take a look at what's called a minor arc and a major arc. A minor arc has measure less than 180 degrees. So a minor arc might be this arc AB or BC, where I can see where it's clearly less than 180 degrees. A major arc has measure greater than 180 degrees. So here I guess I should write down a couple of examples. A minor arc on the one we just did. All right, so for example, looking at the picture we just did, I might say arc AB is a minor arc because I can see that this angle is not nearly equal or greater than 180 degrees. But notice this one. Notice the way I'm going to write this one. I'm going to tell you to go from A to D and stop at C. So it's still an arc. I went from A, D, C. So that indicates to me I've got to go from A all the way around to D and then get to C. Well, since I have gone more than halfway across, I've gone more than 180 degrees. So this would be a major arc. Okay. So we're almost there. Almost there. One more, let me give you an example with some numbers so we can play with it. And then I want to give you another definition of angles, which technically comes a little later, I think, but I want to just use the term now, and then we'll be using it again. So let me give you an example of playing with some of these angle and arc measurements. And then we'll wrap it up. All right, so here's a couple of examples. I've been doing those in blue, so let's keep it consistent. So let's start with a circle. I'm going to freehand it again. Ooh, I'm getting better. That one's pretty good. Doesn't always happen that way, so I'm pretty excited. Okay, so I'm going to give you a central angle. And let's just create this central angle right here. Oops, I apologize for the smear again. And I'm going to tell you that this angle is 60 degrees. And I want to show you a couple of cool things. Because that angle is 60 degrees, okay, and I'm going to call this point A. I'll call this center C this time. Let's think about what we already know right now. We know, based on the picture, we know a few things. We know the central angle, in other words, angle A to C to B. We know that central angle is 60 degrees. So that's the first thing we know, because I told you it is. But because we know the central angle is 60, and we now know that if we have a central angle, it's the same measurement as the arc that it spans, we now know that the measurement of the arc created from A to B is also 60 degrees. All right, so we now know that this measurement from A to B is also 60 degrees. And remember, there's 360 degrees in any circle. But the cool part is, and we don't have to prove it in this class, we're just going to be able to use it, is watch what happens if I take these same points, A and B, but instead of having the vertex at the center, I'm going to make it nice right now. It doesn't have to be. I'm going to put the vertex clear across the circle. And I'm going to go, let's go from B to that new vertex over here to A. Sorry for getting in your way. And we don't have to prove it in this class. I'm going to give you the information. I'm going to call that point D. Well, because I know it is created from the same two endpoints, I know the center measurement is 60 degrees. If I go to any other point on the circle, it's always half of that. So this angle right here, and I'm going to say the following. Since AB is 60 degrees, and angle D is any point other than the central angle, then the measure of angle ADB is automatically half of whatever the arc was that it spanned. So I know that this measurement, measure of angle ADB, is automatically 30 degrees. So I'm going to do it again. I would use the same drawing if we were together, but I don't want to confuse people. So if I give you a circle and I tell you that this arc right here is 80 degrees, I'm going to do this with pictures then. If I go to any other point on the circle, any other point on the circle, I'm going to choose this one. And if I connect these together using the exact same arc, whoops, I guess I'm going to choose this one because it slipped. I'm going to move my point down here. Sorry, guys, my finger slipped. So notice the endpoints still create the same arc. It's still this same arc that's 80 degrees. but instead of going to the central angle, which is also 80, it goes to any other point on the circle, which means it is automatically half the size of the arc. So the central angle equals the arc that it spans. Any other point anywhere else on the circle will be half of that arc. Okay. And then the last little tiny piece, it'll honestly take like 30 seconds. Again, we're going to introduce it a little bit later. I can't remember if it shows up in this section or not. If I give you any two angles that share a common vertex, so notice I have two intersecting lines. We have what are called vertical angles. They do not have to be literally vertical from each other. Sometimes you also hear them called opposite angles. Now let me give you an idea. Here's a vertical angle. I'll call this angle A. Here's a vertical angle. I'll call this angle B. Those two vertical angles, they have the exact same measure. I shouldn't say are, I should say have equal measure. So if one of them is 100 degrees, the other one is 100 degrees because they've been made with the same two intersecting lines. If I give you the other angles, I'm going to call this one angle 1 and this one angle 2. Since they are across from each other or opposite of each other, they are also have equal measure. Angle number 1 and number 2 also have equal measure. All right, so this was a long section full of vocabulary. We'll refer to this vocabulary from here on. So I would make sure you've got those written down, read through them, maybe make some note cards if you like having flashcards or note cards. All right, so that's it for section 11.1. So until next time, have a good day.